Hello, everyone. Hiya, Belarus. Um, Always nice to see people. Bang on 2 o'clock, click on the dot. Live stream starts. People are here. Exciting stuff. Am I actually live? Twitch is giving me mixed messages. Oh no, it's getting there. It's getting there. It's now saying offline and also 45 seconds. Good morning, Mars Nash. Oh, Reed fixed the PC. Congratulations, you fixed the PC. That's good news. We got there. I'm going to assume that I am live. None of this really, matters whether I'm live or not, right? I'm going to learn the maths either way. If you're joining us for the first time, my plan is that I'm going to learn some maths and maybe do that live. Thank you, Herb. Maybe do that live on the internet. What an idea. Quick overview before we get into it. Last week we did a big overview of some maths. We mapped out what was in a big section of some notes, and now I think I'm going to go back and fill in some of the details, picking out kind of interesting things along the way. One of them is this thing called Hensel's lemma. So I want to try and build up my understanding of this. We skimmed it last time through. We're doing fast, slow, fast. And yeah, I want to put more detail in. So, oh my gosh, is in chat. On the way home from an Oxford offer holiday at Somerville. Somebody asked if somebody asked about somebody asked about offer holidays recently on one of the streams, and I'd forgotten they were a thing. Nice to see colleges doing these again. I hope you had a lovely time in Oxford and in Somerville. I only get to meet people when they actually start the course at the start. Which is nice. I get to stand up at the kind of induction at the start of the year and say, "Hi everyone, it'd be great to be ambassadors." Yeah, this is Zoe. I don't know why I read you out as "Oh my gosh," which is it's still Zoe. I vaguely remember that happening. Right, it would be good if this was pre-recorded. If it were pre-recorded, I could skip ahead to the bit where I understand stuff. That would be very convenient. I'm saying a G, right? You can skip straight into the bit where, now we get it. Okay. So here's the ingredients we've got in Hensel's lemma. Hi, Neutrino. There's a percent sign in there. Why is there a percent sign in there? I've done that weirdly. The ingredients we've got a polynomial. It's got whole number coefficients, and p is an odd prime, which is most of them. We've got a solution, mod p, and we're looking for a solution, mod p to the r. And I am particularly interested in the equation x squared plus 1, because I think that makes a good thumbnail, right? You're like, oh, x squared plus 1 has solutions? And the answer is it sometimes does have solutions. So there's a proof. I had a look at the proof again, not on the stream. I did some in Minecraft streams. They say it's off-stream mining, and you come back and they feel like an amazing base. I did some off-stream understanding, where I, in between live streams, went back and reread this. The proof's pretty cool. It brings in some extra letters and notation and stuff, but the proof is essentially just, well, here you go. We can just calculate it. Where are we going? We can solve for lambda. It's sort of explicit in the sense that it actually gets a solution. So I thought instead of reading it line by line, we could do some visualization. We could have a look at it. Particularly this kind of setup where we've got not this stuff up here, but down here. Sorry, previous page. It's literally flipping between different pages, right? Combine things together. So the setup is we've got a solution to a polynomial, and then we're looking p squared. I think we're doing induction. That is the plan. So I have a Desmos for this. Look at me preparing material, preparing stuff. Here's my Desmos. Ooh, yep, there we go. Looking good. What were we trying to get me on? Oh, we're trying to get me on Minecraft. Yeah. One day this will turn into a live stream about me being bad at video games. Right. So I've got a function here. I'm doing x squared plus 1, the thing I care about, but I'm doing it mod n. The way Desmos writes this is to think of mod as being a function with two sorts of parameters or variables separated by a comma. X squared plus 1, the thing you're actually calculating, and then n, the thing you're dividing by, and you're looking at the remainder. And this maybe makes more sense to, like, I don't know, computer scientists or people who like writing their functions like this. I'm personally a bit used to writing mod n at the end of sentences. That's not how Desmos does it. Okay, so I've got my function, which is just square numbers nab 1. And in here I'm plotting it, I guess, for 0, 1, 2, 3, 4, 5, which if you square them and add 1, then you get 1 squared plus 1 is 2. Welcome to Jill Maths. Down here, 2 squared plus 1 is 5, which is 0, 0, and then 2 and 1. And this has got a solution, like 2 or 3 work. So then we can go up to a power of 5, like 25. And the picture's much better in this case of 25. Our challenge here is, here are the remainders when you take x squared plus 1 and divide it by 25. And the thing I would like to find is points where this is 0, which I can see some of them in the picture. Points where this is 0, around here or over there. I'd like to be able to find them. It is quite nice. I've set this up so that I can do any of them. If I turn the grid off as well, then you get this kind of weird, kind of spooky picture like this. Which, let's try animating it. Oh, Desmos. Whee! There's quite a lot going on if you as you animate this out. There's something going on the left, where it's got this quadratic, where if you're doing remainders, mod bigger and bigger numbers, then the small squares, they don't care about that division. What's 8 squared mod 100? Okay, 8 squared. The bit on the right is symmetric, and that's because squaring negative numbers is the same as squaring positive numbers. There's a bit in the middle. Let's see if we can slow this down. Yeah, so this bit in the middle, which actually looks like a parabola, that's interesting to me. That doesn't really make a lot of sense, but hey. And there's some stuff in between that's moving around. Hey, welcome to chat. Hang on, how do you change the speed on Desmos? Ah, there we go. Ooh, I can go really slow. So it is giving me the kind of Space Invaders vibe as well, right? Things. I don't know. It's quite low pixel rendering of something or other. This middle bit that's clearly a quadratic is interesting. The bits on the outside are interesting. The kind of falling rain in between. If you think, I've tried thinking about this. So these bits where it's falling are the result of taking quite a large square number and dividing it by successively larger and larger things. So if you take a big square like 64 and you say, what's the remainder when you divide that by 35? Get something. What's the remainder when you divide that by 36? And you keep going. The remainder is just subtract. What's the remainder when you divide 64 by 60? It's 4. What's the remainder when you divide it by 61? It's 3. What's the remainder when you divide it by 62? 2. And it's coming down. Can people look up their first chat message? Can you scroll all the way back? We don't judge people. Okay. Something else, when I was putting this together just before the stream, I found that you can switch this on. So we can look at x squared. Let's hope this renders. Which is like a join the dots puzzle, right? For x squared, what n looks like. So this is x squared plus 1 mod 77, which is interesting in its own way. 1, 2, 3, 4, 5, 6, 7, 8. No, 0, 1, 2, 3, 4, 5, 6, 7, 8. And then 9 squared is too large, it comes down here. It's not how you would join the dots, right? And the line that it's drawn, which is just you take the parabola, but then keep shifting it down. So that once you get past 77, chop that bit off, bring it down. That's getting steeper and steeper. So I thought maybe plotting this would help me understand the symmetry or the nice bit in the middle, but no. It's pretty chill, right? If somebody gives you a dot-to-dot puzzle, but the top is the same as the bottom. The top's identified with the bottom. Maybe they've drawn it on a big loop of paper that goes off the table, comes back on the bottom. Then you can do your joint to dot by just doing the pin on the left together, and then you see there's a dot down here you haven't done yet. You think, great, I'll just go off the top, hit that one, and then I'll sort of lazily wind my way through several, go off the top again, come back at the bottom, to wrap around again and again. And it seems like it's doing that faster and faster until it's joining up. What if you do it with a Mobius strip? That's not the same as modular arithmetic, so not relevant to my number theory activities right now. Okay, this is not a helpful join the dots. This is the shape that we're trying to interact with, and I'm going to put this back down to 25 for now. So Hensel's lemma says, if you've got a solution mod 5, and provided the gradient is non-zero, we don't really understand what's going on there yet, then you can find a solution mod 25. So you find this number down here, which looks like it's 7. Now I think 7 squared is 49 plus 1 is 50, which is a multiple of 25. So cool, okay, that's 7. So the strategy for finding these says, well, we were starting off with a solution mod p, so we should look at those, and then kind of it was 2 mod p that worked when p was 5. We thought 2 was a solution. Just quickly put this back down to 5. Yeah, of course. So things like 2 work there. And when we go up to looking mod 25, I know that things that are 2 more than a multiple of 5. So here I've got Desmos to do a little list of things that are 2 more than a multiple of 5. I've got some multiples of 5 in here, and I've got plus 2. These ones are interesting to me. They are here. Got Desmos to work. Desmos did the thing. So these are nice because we know that if our number is 2 more than a multiple of 5, then when we put it in the function, we'll get at least something that's a multiple of 5. Said differently, all of these things I've circled, they lie on the multiple of 5 lines. That's kind of the most obvious thing we can say, I think, with the information that we've got. If 2 works mod 5, then, well, you've got all these different candidates, and you might try different things that are 2 mod 5, which in the mod 25 world, there are quite a few possibilities for things that are 2 more than a multiple of 5, 2 or 7 or 12 or 17 or 22. And that's all my list is doing here, really. It's those numbers. And we know that when you apply the function, you get something that's a multiple of 5. So it's on one of these horizontal lines. What we'd like is to work out that one of them is actually on the 0. But they're really nice. So if you look at these, circled ones in red, I want to say they're on a straight line. Do you know what I mean? Maybe it's not clear with just 5 of them, and I should use some larger primes or something, but let's see if chat will accept it. Chat, are you happy if I claim that these are on a straight line? They're clearly not, right? I suppose I'm using the technology again of this thing looping around at the top. So the straight line that I'm imagining has negative gradient and comes back again up here. Let's do it with some larger numbers. While you're thinking about that and whether I can get away with saying that's a 3 is a conclusive pattern, right? That's clearly a straight line within the 80s monster. There's a straight line thing. I'm going to try and put some larger numbers on. Yeah, okay. I haven't proved why. Let's try and make it look a bit more visually arresting. Let's use a larger prime than 5. Let's use 13. Right now, I don't want these ones. Stop. So it looks like 5 is a solution mod 13. So I'm going to take these and I'm going to do multiples of 13 plus 5. We'll have a look at those when we're working in the much larger 169 problem. Oh, this is going to be a great picture. Oh, look at that. That's brilliant. There's so much going on in there. I really like that. Okay. 13 squared is 169. Yes. So we've got loads of values here of x squared plus 1. And my claim is that if I switch these on again to circle the ones that are 5 more than a multiple of 13, then they're going to have to be on the multiples of 13, because we know those ones are going to give us a multiple of 13. Maybe not a multiple of 169, but they should form us in line again. Right, so that's still not that convincing, is it? Is that a line? Is that okay? So Herb thinks that's convincing. Maybe I should try and plot the line. You know, maybe plotting the line would be good for me anyway. Yeah, I suppose. Oh no, there's kind of multiple ways that you could join the dots if you're using a straight line, but with that rule that you can wrap around. What should I try and do? Should I try and give it a go? We've got x is 5, so there's something. Well, I wanted to try and show you there's some nice pattern going on here. That these things are something we could get a handle on to sort of predict. Oh, the ones where you choose, you look at everything that's 5 mod 13, and you see how things wrap around, and you see what the values of those things are, mod 169. Hopefully they'll be nice and predictable, and you'll get a solution. There's one down here. This is what we're looking for. We're looking for this number. What is that? 60. 70. 70, which is a solution to the problem mod 169, because I think, he says, frantically checking, that 4,901 is a multiple of 169? Is that what I'm claiming? That is what I'm claiming. It's 29 times 169. Cool. So, yeah, the kind of silly punchline that I've been doing is, so that means that -1 is a square number for mod 169. It's 70 squared mod 169. 70 squared is the same thing as -1 in the mod 169 world. Yeah, so I think in order to understand the lecture notes, we're going to try and understand a very particular straight line that goes through these. It's not the straight line that I was first thinking of, because I think the lecture notes are going to talk about the gradient at this. So looking at this first one, looking at the gradient there. So I'm going to try and draw that line. How am I going to do that? It's going to have to be x minus 5, and there's some gradient here, which I haven't decided what the gradient is. Plus, and then what's the value of 5 squared plus 1? That's 26. Add a slider for the gradient. Okay, so it's going to go through this point. I think we're going to make sure it has the same gradient as the quadratic, which would be 10. Yeah, that's it. So this is suspicious. This is the tangent to the quadratic, which is like a random line to choose. I think this is the line, or this is one example of a line that's going to go through all of these points, with the rule that we're going to wrap around every 169. So what do I want to do? Something like this. which is the tangent to the quadratic at that first one. But I want to do it mod n, I think. Yeah. So that's not the line people were thinking of. Kind of at all. Sorry about that. Yeah, the line in my head was also different. What have we learned? Always an opportunity when some maths does something that looks kind of like what you're imagining, but not quite. What is this trying to do? So this is trying to go through all of the points in the right order with a kind of wrapping around, which is no, I was imagining something coming down. I suppose I was imagining something where, wait, does this work? So the gradient, we could also maybe think about this being mod 169. So maybe if I make the gradient minus 159, that was a mistake. Why did I do that? That was a terrible error. Don't do that. No, yeah, okay, I regret that entirely. Let's just colour the screen in green. Nobody wanted that. It's weird. What is this? So what is this gradient of the line that would come down through all these points? That'd be interesting. I don't know. It's not just minus, is it? Worth a try. What do I want it to do? So instead of going up by 10 units every 130, I want it to come down by 39. Try to do some quick maths. Oh, that was almost it. That was it. 3. Okay, that was the line in my head. We got that. Is this the line other people are imagining for like a join the dots puzzle? 3. Yeah, okay. With like the wraparound rule. Okay, the one in the lecture notes is definitely this one. So this is where I'm trying to get to, like the tangent to the quadratic. Ooh. 10 and minus 3 are the same thing mod 13, which I think might be relevant. So I think if I put anything in here that's minus 3 mod 13, so test my hypothesis a little bit by putting in minus 16. Right, okay, so the joys of modular arithmetic, there's a kind of family of lines that we can use here that go through all of the points with kind of different gradients going on. There's one with a really shallow gradient. What's going on there? But it's a shallow gradient for every, that would be every 1, 2, 3, 4. That's cheeky. Positive 3, no. This is fun, just try different values until I find an interesting one. So that one's interesting. Oh yeah, so we're imagining this line like 0.5 business. It's really shallow kind of line, right? Even more shallow. Like this. Yeah, that sort of thing. But wrapping around the other way. That's something, because visually that works as well. Less keen on that. That's the inverse of 4, which is the inverse of 4 is minus 3, right? Mod 13. Maths. Yeah, 1 over 4, because in the mod 13 world, the inverse of 4 is minus 3. I'm confusing myself by switching to 13s. Anyway, the way this proof is going to work is that we're going to work out a predictable jump from one of these circle points to the next one, and then just extrapolate that until it hits 0. It's a bit like Newton's method for finding roots. If you've spotted a straight line, you can extrapolate it to find where it hits the axis. That's the case here, even though the line like wraps around because of the magic of modular arithmetic. Does this sort of looping thing. Okay, I'm extremely dissatisfied with this line. I think I want some sort of refund. But we are going to go back into looking at the lecture notes and see if this helps us understand. Screen share is no longer active. Connect to app. Close? No? Okay, we're not going back into the lecture notes. We're going to look at this a second more. Accept connection? Nope, not happy. Technical pause. Best kind of pause. Now it's happy. There we go. Whoop. It's a complicated tech setup. They do look like Rorschach tests. I already thought that they looked like Rorschach tests before you said that. I think it's the symmetry. It's the way that they have, like, there's clearly some shapes or logic to it. But they're abstract. Let's turn the axes off again. Let's set this to a different number. Ooh. Tell me what you see. Great disclaimer, I am not that sort of doctor. What's a nice number again? We like 25 a lot. Little smiley face up here, up the top. Good, right, I don't think we're derailed. I think the point of doing these diagrams, or the point of visualizing things, is that it brings in the part of your brain that joins the dots and spots patterns. I'm genuinely interested in this like quadratic shapes bit here. What is going on there? What is going on there? It's really good. I kind of want to understand that, right? To understand why it looks like a quadratic up there. And I wouldn't have thought of trying to investigate. Oh, what is that? N over 2. Symmetry around the N over 2 line looks like a quadratic. What's going on there? Wouldn't have thought of investigating that at all unless I'd made the image. I thought about what I could see. So I'm not knocking it. It's genuinely a stage of maths, I think. Ooh, that's got all horizontal bits in. Is that 108? Interesting. Should we set some famous numbers? 163? Yeah, it's pretty good. Good, okay. Okay, I kind of want to get sidetracked and think about N over 2. Do some sort of live maths investigation. I think the trick is going to be not to think about this, but to think about a shifted version of that, like a Taylor series. And that links in nicely, actually, because we're going to go and look at a Taylor series now. Hey, it's working again. Hi, everyone. Hi, Mary. Was there a cat in there? Ooh. Mary, if you've just joined us, we're looking at something from last week. We made a visualizer. We got distracted by other stuff that we could see in the visualizer that reminded us of other things. But now we're going back into the maths. Okay, so boring base case, but then there's an inductive step. And what is this? Oh, there's a condition in here that I haven't mentioned yet, which is the derivative is supposed to be non-zero. That'll be all right. I'm only interested in x squared plus 1, which has non-zero derivative, except in some special cases. Okay, so we have this. I'm going to really be thinking about f of x1 equals 0 mod. Oh, what do I want? I was going to say p. Oh yeah, so if r is 2, then it's this. And what? Oh, they're all equivalent mod p. Okay. So this statement doesn't say anything if r is 2. It just says x1 is equivalent to x1. So that f prime. Yeah, okay. Inductive steps are irritating because we have to have this variable r in here. I only really care if I can make it to p squared, I think. Oh no, I do care about p cubed a bit, I suppose. We should be able to keep going. To make it easier on first reading, I'm going to take r equals 2. I want to see how we get from 5 to 25, how we get from 13 to 169, and then reread it for general R. Okay, then this says that f of x1 is k p for some integer k. Cool, that says it's a multiple of p, which we know. F of x1 is equivalent to 0 mod p, that means it's a multiple of p. So now consider, well, lambda is an integer, right? What is this? Consider x2 equal to x1 plus some lambda p. Add on some more lambda p's. Okay, so these are the other ones that we circled in red. We had x1, like 2 mod 5 or something. Plus lambda times 5. So multiples of 5. And those are the ones where we know the value of f. Right, next page. Quick look. These things are equivalent to x1 mod p, because I've just added on a multiple of p. Maybe it was 2, now I'm looking at 2, 7, and 12 and things. Now, here we go. F of x2 is the same thing as f of x1 plus lambda p. So that's what we did. We added on lambda p to look at not just 2 mod 5, but also 7 mod 5 and 12 mod 5, searching for one of these to be a solution. That is a Taylor series. Okay, so I'm imagining f is x squared plus 1, which means that this thing is x1 plus lambda p squared plus 1, which is x squared plus 1 plus 2x1 lambda p plus lambda squared p squared. Which I guess, okay, so it's f of x1 plus something to do with the derivative. Ooh, everything went there. Oh gosh. Yep, we're good. Something to do with the derivative, and then lambda squared p squared. So if I'm working mod p squared over here, then what can I do? So Taylor series. Okay, so working it out for x squared plus 1 is like slow and boring and uses the binomial expansion. Really, I should be thinking about a Taylor series. I would be happier if, yeah, okay, so slightly more general. Let's have a go at slightly more general. F of x1 plus, here it's lambda p f prime of x. That's the difference, the amount we're moving. Plus, and then lambda squared p squared over 2 f prime prime of x1 plus, and this is a sort of finitely many things. I guess we have to go to the degree of the polynomial. Degree of the polynomial? Yeah, because at some point these derivatives will be 0. So it's a Taylor series, but it's only got finitely many terms because it's polynomial. Okay, that's not very important. There's loads of powers of p squared here. Yeah, right, okay, so they're doing this p twice r minus 1. Oh, I see, so if we're imagining generalizing this one step more, so this is me focusing on r is 2 for my first read through. Apparently you've got to think a little bit about how you get to r p cubed, how you do the r equals 3 step, slightly, the logic is slightly not what I would have guessed. That's a fact about what's going on in my brain rather than a fact about what you're looking at, but that's not quite what I would have intuitively guessed. Anyway, I thought it was always lambda p. That's the thing that's changing with r. Okay, welcome back to James is an Idiot. What are we doing? Oh yeah, so this f of x1 is 0. I underlined it, it's 0. So we're just left with this much stuff. And what do they know here? Oh no, this thing's not 0 mod p to the r. This thing, it lies on one of the lines, one of the horizontal lines that are kp mod p squared. Do we have a letter for that? We're saying lambda for the shift we've done that way. Are we saying, yeah, k for the shift up? Okay, so we're looking at our original solution, 2 mod 5, and we're thinking about going lambda along. Look at other things like 7 and 12, and we're also thinking about working up. The function at the first one is a multiple of p. The function of all of these is going to be a multiple of p. P here. If R is 1, that just says, oh no. If R is 2, that says P. R equals 2 on first reading. Then this is multiple of P. Kp, what it was before, plus some amount, lambda f prime. So this is where I got the 10 from in the previous, when we tried to join some dots. Now, what else is true? Because we messed around with other things, so as well as putting 10 in here, so P, K plus, and then here lambda f prime of x1. So we saw that this is the f of xr. xr depend on lambda. Yeah, okay. For each of these, whatever lambda is, this value of the function depends on everything like this. So, okay, so you could change f prime. You could write f prime minus p here. This is what we did, and then that would be equivalent. There's a, because all I've done is subtracted lambda p squared. R is 2 on first reading. So this is why we had a different ways to join this line. We had f prime, which works because of weird Taylor series stuff. The next term involves p squared in a Taylor series. I've written out this Taylor series in such a cramped mess, but it's more for getting my brain to work on what Taylor series look like rather than presenting a Taylor series. So this is why the line we tried a line with gradient -3 instead of 10 back when we were trying prime 13. That checks out that both of those would be consistent. They would go through all the dots. Anyway, we want this to be 0, so we should choose lambda such that this bracket k plus lambda f prime is 0. If f prime is non-zero, it's got an inverse. That's what you should choose lambda to be. So I kind of want to write lambda is so solve for lambda, but we can make this a little bit more explicit, right? So lambda is minus k over f prime. Oh, that's not really what people don't really write that for like the inverse. And then xr. So what's x2? So if I'm being explicit in the margins, in the sense of writing out what things actually are, then the plan was to write x2 as x1 plus lambda p. Kp, that's the value of, yes, that's the value of f of x1. That's exactly Newton's rule. Newton's method. So Newton's method in A-level tells you how to take a solution. You're imagining you've got some sort of polynomial, you're looking for a root. What a terrible picture. So you start with a point here, and you say, well, if I work out the gradient at this point, then I'll get a pretty good impression of where to look for a root. I should follow the gradient down to the axis, which in this case would say take your x-coordinate and subtract an amount that depends on how high up you are and what the gradient is. There's a little triangle there. That's exactly the same rule because this is linear. Yeah, so this lambda is code for the kind of input, independent variable, and then the k is the value comes out. Yeah, we're accidentally revising A-level mocks. Weirdly, sorry about that. Newton's rule's pretty good. If you work here, you go, whoa, I found a solution. And then you can do it again. So this is pretty close. And then you can follow in again. And then you can follow in again. That's just brilliant at getting close to roots. It's quadratic, I think, in terms of the speed of convergence, which is pretty good. Yeah. If you're accounting your time, then this is a reminder that Newton's method. Yeah, cool. Same formula. Really quick triangle revision so I can make sure I'm actually doing the right thing. If this is f of x for x, then the gradient, we want to do this like delta thing here. So if I call this d for the distance you're supposed to move, and I think this is true, f of x divided by d is f prime of x. Right, that's where the f divided by f prime, and I should subtract this distance from x in like diagram dependency. This is where I've got this vertical gradient thing. So the guide here is to subtract f of x over f prime of x from x. That can go terribly wrong, especially if f prime is 0, which this formula will then say, well, subtract infinity, off you go to negative infinity, see if you can find a root over there, or just if you're too far away. So if you start here, then it says you should go sort of sideways a bit and then maybe down a bit. It's sort of, you might get lucky, or you might just wander off to infinity if you're nowhere near the root. But it works quite well in terms of like tangent following, which makes it a tiny bit like gradient descent, but not really. Kind of gradient descent. Anyway, sort of 1D gradient descent. Is that true? I need to revise this separately. You know, reading what's going on at a single point, trying to extrapolate to say, can I just like find a solution nearby? Let's go. Okay, so it's pretty cool. The algebra doesn't quite line up with the pictures that we were drawing. Really? Does it? This inverse is interpreted mod p squared. But good enough, I think. Okay, let's reread it once more, but with r, not necessarily 2. So what changes? I think the things that change should be everything goes up by, for the next one to find something, a solution mod p cubed, everything goes up by 1. That Taylor series is slightly different because the things we're looking at jump by, right. We're supposed to look at different values of xr that differ from where we were for our previous solution by lambda times p to the r minus 1. That also goes up. So to find a solution mod 125, having found 5 and 25, solutions mod 5 and 25, to find a solution mod 125, right, okay, so we've got something that works mod 25, so we started looking at the 5 possibilities of, these 5 possibilities. We know that they're going to work mod 25, so they're going to be on these horizontal lines mod 25, and you'll split them out by distances 25 across, nice and evenly split. Let's have a look at those just to check. So I'm going to set this to 125, and I'm going to set this as my little device for looking at a particular subset of the points. In here we can look at things that are, what was my solution? It was 7 mod 25, so things that are 7 more than a multiple of 25. Okay, there's 5 of them again, but again they form some sort of nice straight line. The derivative here is mad. I'm clearly in some sort of nice, maybe it's not as simple as we're going to find a straight line that visually just goes through these points, but there's clearly some sort of like rhyme or reason to where these points are. They think something pretty systematic on a kind of grid. If there was another one, it would be here, lining up with that one again, right? Everything's kind of evenly spaced. It's very nice. Okay. So now I should imagine jumping by multiples of 25, and these things, we know they work mod 25, but do they work mod 125? Note to self, if you're trying to teach this to someone, do not pick 5, because all of the powers of 5 sound the same. I'm having to really stress 100 and, rather than, I just get confused between 25 and 125, like me. Where are we going? In here. Stick to like 13, 169. 169 is quite hard to say. What's the best prime for this? 11? 1 to 1? Because 1 to 1 sounds like a phrase, doesn't it? I need a number where not too big, an odd prime that's not too large, and its powers are Easy to say. It's going to have to be 3, 9, 27, isn't it? Oh, 3's rubbish though. It's almost everything. Quick check on 3. I say 3's rubbish. And then 9's not that interesting. So in here I should be, ignore the circles. The circles are custom built for mod 25. Yeah, I don't like that at all. 12 is not quite an odd prime, but I agree that 12 and 144 sound nice, are easy to say. So points there. Plus the next one's 1728, right? So that's pretty good. Yeah, good. Which is a number worth saying quite a lot. Oh, I like 17. I like 17, I think. Yeah, 289. 4913. It's pretty good. Pretty good. Let's quick look at the picture mod 17. It's pretty nice. It's definitely a little guy. A little guy with really long arms. And a big smile. Sorry. Most books has put me onto interpreting these as little guys. So happy to see that's right. Hello, and it's 17. So if we've got a solution mod 17, and it looks like, where's that, 5? Where's that, 5 mod 17? No, 4 mod 17, because 16 plus 1 is 17. There it is, there's the solution. Oh, I was imagining some of these as like arms, and then these are like the little legs. This is like torso. Hang on. Like this. He's so smiley. He's here to help. Good. Right, quick up to 289. Herb's suggestion of prime. Mate's book's suggestions of interpreting them as monsters. Oh, that's just so clearly like straight line stuff. Brilliant. Oh, 289 is really good. I should name the little guy. Mod 17 monster needs a name, doesn't he? I'll let chat be in charge of that. Okay. There's a solution straight away. Well, not quite straight away. Okay, so where do we find that? We're supposed to take 17. So back into the notes, please. Yep. 17. I was trying to think about cubes, but I'm just going to go back to think about 17 quickly. So I had 4 mod 17, so I'm supposed to go to 4 minus, and then here I put in the value of 4 squared plus 1, imagining that mod 289. I know that's what's going on? Why does everyone want to call it Sven? Oh, chat. So I kind of need the inverse of 8, which I don't really want to calculate. Mod 289. You can do this as sort of just an exercise in Euclid's algorithm and Bazoo, but it's not very fun. Why are we calling it Sven Tennant? I love you, chat, but what are you doing? You're not the same person? Hang on while I just Google Sven Tennant. Yeah, I think that's an original creation of chat. Cool. Cool. Sometimes I worry that doing a maths live stream is a bit weird. course it is. Right. Okay, so I was just going to read this through one more time, but with p a larger number than, with r a larger number than 2. The jumps work like this, and this is the only step then that I think I'm confused about. The Taylor series brings out a factor. Oh, it is a factor of p squared or p cubed or whatever. And then the higher order terms, let's think here. So the next term in the Taylor series, right, it kind of is way more. Here I looked at it, and the next term is p squared in my Taylor series because I was doing a jump by p, and then the Taylor series thing says to square the jump that you're taking. It's like x minus x naught, right? How does this work? Taylor series like this, right? And then the next thing is to square that difference over 2. This is definitely a level revision. Taylor series written up neatly. Oh, Sven as in 17. Okay. Sven-17. Brilliant. Great. Okay, so I saw this p squared and I thought that's the next power of p, but that's a coincidence that in that case, squaring meant multiplying by p. In general, it's even more because the jumps might be like p squared or something, so then this would be p to the 4. Or the jumps that we're looking at, the kind of shift that we're looking at horizontally to get between those different red circle terms might be like p cubed. If we've got quite advanced, then p to 6, which is definitely enough. We just need it to be like one more power of. We just needed one more factor of p in order to ignore it in our modular calculation over here. Okay, so that's the thing that worried me that the step from this term of the Taylor series to that term is not just multiplied by p, it's something actually better. So square the size of your jump. Okay. Yeah, no, I thought that was just like random. I thought the kids these days they want to name things Sven. I don't know. Don't know why I thought that was going on, but yeah, I thought 2 random people in chat both said Sven because of their a sort of meme. Cool. Got 2 cursors going on, which is not quite how many cursors you want. Good. Okay, jumps, and we're all good. So then it's still the same sort of rule because that's the jump there, and it's lovely. The size of the jumps that we're looking at is the same as the size of the output steps. That's kind of k p to the r minus 1, but also a lambda p to the r minus 1. Those are both the previous problem that we're solving, sort of smaller square. You say your solution lies on the x-axis in this small square, and then to go to like the next problem up, which is to multiply by p and look at larger numbers. You get this larger square, but it's larger by kind of tessellating pictures around. I don't know. So multiple of p in both directions. Good, right, okay. Chat's really broken me by all saying Sven at the same time. Great, cool. Okay, I think I'm happy with this. There's a little footnote about the number, the prime 2, which I'm going to read because I want to be done with this section 39 or whatever this is. But wait, this is we have proved. Okay, let's get there. What is this? P or prime? Yeah, so this is the particular calculation that we're interested in. Yeah, okay. We've been using x squared plus 1 as a solution, so I'm happy with this. Yep. What happens when p is 2? Clearly there is a solution to v squared is minus 1 mod 2. That is v equals 1 mod 2. Odd numbers squared to minus 1 mod 2, because minus 1 mod 2 just means odd. If the power is bigger, then a solution to that would be a solution mod 4, which doesn't exist because... oh, right, we know the square's mod 4. Sorry, being daft. The square's mod 4, well, your number is either 0, 1, 2, or 3 mod 4, and when you square it, you get 0, 1, 0, or 1, but you never get 3 or minus 1 mod 4. Okay. So that says you can't go to the next power. If you were looking at an even prime, then you can have a solution to the polynomial here, but you get no solution mod 4. And then you get no solution mod 8, because a solution mod 8 would be a solution mod 4. Woof. Can I do this differently? Because it feels like the reason why you can't have squares like that. So this is something like v squared plus 1 might be even, but never a multiple of 4. And that's not actually very hard to prove. I mean, we kind of did it just now by thinking about the possibilities. But yeah, that's all we're saying. V squared plus 1 might be even, but never a multiple of 4. If it is even, then it's not. If v is even, then this is not even an even number. But if it is odd, then you get 4k squared. So if it's 2k plus 1 plus 4k plus 2, which is definitely not a multiple of 4 for any value of k you think of, because these first bits are a multiple of 4, and then that bit's definitely not. Okay, so that's kind of cool, that v squared plus 1. Think of a square, add 1, that might be even, but it's never a multiple of 4. Okay, right. Okay, this was part of a bigger picture where, I mean, in the lecture notes they're trying to work out which numbers can be written as the sum of 2 coprime squares. I'm kind of really interested in the special case where one of those squares is the number 1, but there's some more theory in here to try and do this case of two squares. And then just over the page I remember there's a bit about looking for just the sum of 2 squares. What's the difference between those two problems? Product of a square and a number that is the sum of 2 prime squares. Oh, so you can put extra squares in there. Yeah, so that's then the statement 41 is just looking at the kind of tricky primes. Okay. I'm getting there. Yes, and if and only if all the way through for 40 and 41. Yeah, suppose it's the sum of 2 not coprime squares, take out the factor. That must have been a factor of your original number. Keep going, yeah. Now you've got 2 coprime squares equal to the sum of something. Okay. Right, I think I need another target for a thing to understand. We're about to hit 3 o'clock, so this is excellent timing. I'm gonna redeem the hydrate thing. Can I actually redeem it? Trigger the thing. I can. Maria's on. Maria's done tea time at the same moment. So I can, beverages everywhere. Okay. Well, how am I going to do this? This is a quick break at 3 o'clock for me to get my breath back and make a cup of tea. I'm going to run an ad break. If you see any ads, you're supporting charity, because I don't really understand Twitch, but any cash that Twitch gets for this stream, well, no, hang on. Let me be really careful with the phrasing here. For all I know, Twitch is getting buckets of cash constantly that they can give to Amazon and stuff. But if they give me any of that money, then it's going to charity. So the adverts that you see sort of support charity a little bit, in that, who knows, if you buy a new TV as a result of the advert, then some of that TV money gets obviously spent on making a TV, but some of it trickles back to Twitch, and then Twitch give some cut to the people who make streams. That was a long way of saying streams. If you don't want ads, you can sub. If you have Twitch Prime, then you can use your Twitch Prime sub to avoid adverts. If you have Amazon Prime, then you have Twitch Prime for free. It's an included perk in Amazon Prime. Each month you can subscribe to one Twitch channel. You have to keep redeeming it every month. It's slightly annoying, which reminds me that once this stream's over, I'm going to go redeem my Twitch Prime sub on somebody else's channel. I think you're not allowed to use it on your own channel, that sort of thing. Right, cool. I'm going to leave the kind of cool maths on screen. I think it's the same cool maths I left on screen last week. It's this cool proof structure thing. Run an ad, turn the microphone off. See you in a minute with a cup of tea. Little information box. You recently ran an ad and must wait to now run another. Oh, I didn't want to do. Okay, right, good. I think we're back. We lost a lot of viewers. We lost a lot of viewers to adverts. Possibly spending 5 minutes explaining adverts. Ooh, Hermitcraft. Oh, Neutrino's been. Oh, this is a chance to promote like Cat Does Maths. Who else do I like? I like Loading Ready Run. I think Loading Ready Run is the channel I most recently used my Twitch Prime thing on. Canadian sketch comedy, streaming, everything. But they're just nice Canadians. I've actually got Instant Coffee up. Does anyone in the chat have recommendation books videos on how children start to learn maths? I don't know. Like developmental stuff. Fiveness is a really good word. I remember. So I've been listening to some podcasts about teaching in schools, with ideas about how people learn and memorize things. Because it's the sort of thing I'm interested in. I haven't worked my way back. I'm kind of working my way back through the age ranges until maybe one day I'll understand early years stuff. I think I'm supposed to link you to Espresso actually. Well, that hasn't worked, has it? If you just Google the word espresso. Espresso's all age ranges, but it's little digested bits of research about how children learn maths. Yeah, so I don't know if this is start to learn maths, but yeah, it's got ideas about developing, for example, hang on, let's do it quick. This is totally normal thing, like how do people develop concepts of pattern sequences? So here's an image from Espresso. What do you see here? What's the same? What's changing? like kind of visual processing stuff that I've been talking about just now. I think people have done actual research with children on what they're doing. And if you'd like a summary of the research, Espresso is good for that. I guess I'm assuming that Emmaus is interested in how children, maybe because they, I don't know, are a teacher or work with children or just interested in development. If on the off chance that Emmaus is a child, then don't read the Espresso research. If you're interested personally in learning about the concept of 5, I just don't really get that vibe. Good, cool. It's puzzles. Enrich. So Cambridge do a lot of interesting early year stuff. The Cambridge PGC is really good, and they have Enrich and the Millennium Maths Project. So I'm a bit jealous of Cambridge's early years support stuff, like puzzles and problems for young people. Yeah. Right. Okay. What we'll be doing? Oh yeah, we just kind of got our heads around Hensel's lemma. Let's check I've got the name right. I need to be much better at learning the names of things. Hensel's lemma. Let's get it out of my head because the name reminds me of Hansel and Gretel. Hensel's lemma. Let's find out about Hensel. Match. Here's Hensel. I'm on MacTutor, which is the go-to history of mathematicians biographies page by St Andrews University. Hensel invented the p-adic numbers? What? That's a good summary. That's a good summary. Here's good, Hensel. What do you need to know? Invented the p-adic numbers. Oh, okay. 1861 to 1941. I guess should I be impressed that there is a photo? 1861? 1941, yeah, photos. I don't know why I clicked. I should have seen the word 1 and thought, yeah, it's the same picture. Anyway, I'm skimming, but mostly I'm trying to show you that MacTutor is a good place to learn about things. Right, this is in German. Well, the paper titles are in German. Oh wait, what does this do? You can click on T for a translation. Algebraic functions of one variable. Cool, okay. I think I prefer MacTutor for biographies over like other places where you might find descriptions of mathematicians. Like a consistent tone. What's this, about 500 musical compositions? You can't just jump in the middle of a paragraph, can you? The Mendelssohns. What? Okay, I'm trying to skim read and it's not going very well. Yeah, okay. Yeah, I'm currently in a education and learning and what's the right way to actually teach people things. Mood as well. Good, right, okay. I'm enjoying this biography of Hensel. Hensel's lemma. Good stuff. P-adic numbers are also all about powers of primes. Yeah, it's biography is great, right? Why else Mendelssohn here? What? Right. Okay, let's look at our map. Last week we made a kind of map. Maybe map is pushing it, but we've got this list of stuff about quadratic forms. This is kind of the wider context of Hensel's lemma. Gosh, my handwriting's bad. It looks like a spider. It's not had a good day. Yeah, so there's Hensel's lemma. Let's make that a bit more legible, my word. Art and writing, things that I'm not good at. Welcome to the stream. Okay. So, what was all this stuff about properly representing n if and only if equivalent to a form with first coefficient n. That doesn't seem very likely. That can you write n as the sum of two squares? Well, no, wait. Can you write x squared plus y squared to rewrite that in the format n something squared plus 1 plus something? Ugh. Where do I want to jump in next, I think is the question. Oh yeah, we had a disappointing week last week, didn't we, when we found out that x squared minus 2y squared is not an example of something in this section, because it's not positive definite. So I feel like the first bit is not exciting to jump back to, because it's kind of the fundamentals of quadratic forms. And the last bit is too complicated and I don't understand what's going on. So I'm trying to pick somewhere in the middle to jump to. I think it's... I just want to say it's 25, 26. Finitely many reduced forms of discriminant D, although that was, I remember, a little bit of a slog. We did a little bit of calculation for that. And let's think about this representing n. Yeah, I think it's probably 25, 26 where I start to think I've got no idea what's going on. 26, 27, yeah. And then maybe one day we'll get to page 28, which tells us about quadratic residues and n being probably represented by some form of discriminant D. If you know there's only one form with discriminant D, only one reduced form with discriminant D maybe, then you're good. Okay. So I'm going to jump in at page 26, I think, to think about this represent again. If it's not making any sense, I'm going to go back a bit, and if it is making too much sense, I'll be very happy. Hi, Super Snowman. Choosing where to jump on the kind of binary search of where my understanding is. People sort of draw these kind of diagrams like things I know, things I don't know. This is like zone of proximal development, which is like things you don't know, but that are closely related to things you do know. And the idea is you can expand what you know, and by finding this zone somewhere in between, and trying to think about that stuff, which is one of those like artsy diagrams in a way that kind of just makes sense. But I'm trying to be a bit more like mathematician about it. Like if I had a region of space and an exterior point and I wanted to find the boundary, I would do some sort of binary search where I'd have two examples and I'd check the midpoint. So here I do know this, I don't know this, I would check the midpoint. So I'm going to go and look at the midpoint, find out if it's in my zone of proximal development or not, and then just keep going. I might be taking quite a literal approach to the ideas of your experience and understanding being in a diagram, but whatever. So we're going to jump in there. That seems to be about page 25. A lot of chat to avoid actually looking at page 25. Let's go. It doesn't quite work. I mean, in some sense you've got to read it in the right order because it's cumulative and it builds up. But understanding doesn't really work like that. It's rare that you read maths and you understand it all in the right order. Reading maths is not like reading a book. You just saw me reread that proof like 2 or 3 times in the first bit of this stream where okay, 3 separate things. Where did I get this? The document that we're reading. The document that we're reading is from several years ago. Just checking I can find the lecture notes. I cannot find the lecture notes. Oh no, I linked them before, didn't I? 2 seconds. What are we on to here? Theorem 34 looks fine. Okay. Maths notes, yeah. And then number 3. Yep, good. Found it. Okay. I'm sued by someone called Gareth who takes notes in all the lectures they go to, have been to in over the last like 20, 30 years, I think. They sort of still around Cambridge doing some teaching, I think, and sometimes still going to lecture courses. They have notes from different courses they've been to over about 30 years, which I like. Good. Okay, what do I want to read here? I think I want to try and jump in and understand Theorem 34, see if it's something I can understand or not. Okay, every such form. Oh, okay, so already by lemma 32, what was lemma 32? Probably every form is equivalent to a reduced form. It suffices to show that no two reduced forms are equivalent, so that we can put this word unique in. This is like the new content of Theorem 34, I think. Suppose that we've got these are equivalent and reduced by lemma 33, the smallest non-zero integer. Okay, so sort of classifying them by looking at the smallest non-zero integer represented by f is a. Even though, yep, because you don't have to add stuff if you don't want to. These terms are, what, always b positive? B is smaller than c, so if you have some negative term here, then you get more positive stuff over there. Anyway, there's a thing, lemma 33, to say that the smallest thing you write is a, the smallest thing by f prime is a prime, so they're equal. And then here are the values. And then looking at the next ones up as well. What's going on? The four pairs must correspond. Okay, so I've done my looking halfway through between the points, and I think I don't understand what's going on. Four pairs for f prime. Oh, this is the way that if the things are equivalent, then you can match up the values. It's saying there is some x and y such that it takes the same value, so we can find, starting from 1, 0, we can find some x and y that corresponds. Same discriminant, so same sort of b. Oh, but actually there's plus or minus. Oh, we had this at one point, right? We were looking for reduced forms. Yeah, we were looking for reduced forms, like up to 163 or something. With discriminant 163. Okay, if b is 0, then who cares about this plus minus sign? B prime is equal to 0 as well. If b is bigger than 0, then these can't, because, oh my goodness. There's a strict inequality in the definition of a reduced quadratic form. Gosh, this is a memory test from things I read last week, which, if I was reading in the right order, would be right there. So, oh my goodness. If and only if that, and if and only if that. What is this? Checking the values again? Likewise. Oh my goodness. And this is then going to check that the way that they're equivalent is that you have some matrix relationship like this using SL2Z, which is determinant 1 on that matrix of integers. Then, oh my goodness, so checking that these work out. Fine, okay. So it's this plus or minus, so b is minus b. What was all this? So what was all the cases for? Okay, so I think this doesn't make sense to me. Really, at all. I don't know what's going on. I don't know why the points have to correspond to each other. I don't really know what correspond means, I think. And I don't understand the inequalities on A, B, and C. Okay, so back to the map. Good to look at it. To think about why these things might be unique reduced form. Turns out I don't understand it. It's recalling. Probably all this stuff in between I don't really understand. It's possible my things I know graph comes around and does some other stuff as well, but maybe I can find something in between that I do understand. It's possible that I don't understand any of it, right? In which case my zone of proximal development has to be start at the start and just read stuff. I think I know about myself. What do I think? Discriminant 0, 1 mod 4, that's because it's b squared minus 4ac and I know about b squared, that's fine. Over here, Positive definite? Yeah, so I think I didn't really understand this reduced form. Let's go and look at that. Positive definite I remember being... Oh, no, spot test. Can I remember what positive definite is? It's the one where... so we need AC to be positive. If B is 0, this is like saying B squared minus 4AC is negative. Okay, so something like determinant's negative and A is positive. Positive definite. Oh, that took a lot of remembering. I'm going to give myself a tick, but then sneakily go and read it. So that, you know, chat knows. Good. And maybe all those matrices that are coming up, maybe I should go and look at that as well. Okay. But I think we've got a clearer idea of where the interface of things I don't understand is. Thanks for coming on this journey with me to learn new things. We're working backwards a bit. I'm going to have a quick look at the equivalent form again thing on page 20. I'll admit it, things early on in this section have not stuck in my memory, so back we go. Be really interested if anybody wants to use this sort of technique on A-level revision. You know, find things you don't understand, search around for what they're related to. Let's see your Maze books. Have fun. Have a nice afternoon. Thanks for helping to name the Sven monster. I've gone way back. I've gone way too far back. Let's speed run through again. Unimodular substitution is like this, where A is in SL2Z. Okay, there it is. One's with determinant 1. And equivalent if they're related by one of those. Okay, so the definition of being equivalent is not about taking the same values. Oh no, that's the point though, down here. Right. So then we would write that these things are equivalent. I'm struggling with this. Oh my goodness. Does this mean that these matrices should be equal? I think it probably does. No, maybe not. No, it's just telling me that these things are equivalent. Sorry, I'm not supposed to calculate this or prove anything about it. This is what it means to be equivalent related by unimodular substitution. Unimodular substitution like this, related by, yeah, okay, once again. Up. Related? Has that got some special meaning I've forgotten? No. So if you make a unimodular substitution in your quadratic form, then that's like having, so going from, so the substitution would go to A, px plus qy squared, plus B, px plus qy, rx plus sy, plus C, rx plus sy squared. So then that would give us something like an A prime in there somewhere if I calculate the x squared coefficient, which I don't particularly want to do. Okay, so these things would be related. And in matrix terms, we're doing this. So I suppose this is telling me these are the, if you multiply these matrices, these are the coefficients that I'm calculating on the right, with some dividing by 2 going on as well for fun. That's not obvious to me. Yeah, I'm really worried about all the extra terms, but this looks like the change of basis kind of thing that I've seen before, so I think I'm going to not worry about it too much. point is that equivalent forms represent the same numbers, because once you've done the substitution, anything you can write in this form using integers x and y, and then the coefficients, the horrible coefficients that you get from multiplying this out with values of x squared and y squared and xy in your quadratic form, you could combine these things into the brackets, px plus qy. Oops. Oh no. Yeah. Combine these things together into the brackets to get an expression in terms of these are the integers, px plus qy is an integer that you should put into a thing squared plus b thing plus c thing squared. So if you calculate these integers inside brackets, then you get integers that you should put into your ABC quadratic form. And then going the other way uses the inverse matrix. But because the determinant's 1, the inverse is nice and simple. It is, how do you do the inverse of a 2 by 2 matrix? That's what you want it to be or something. But the point is that the inverse exists and it uses integers, which lets you convert back to say, aha, if you've got some solutions, you are planning to plug in particular numbers into this quadratic form. Well, I've got a plan for you. Please convert your integers into these other hideous integers using this inverse matrix and plug them into this mad quadratic form. If you do that, you'll get the same answer, which is a bit of a weird proposal, but hey. Okay. Right, I've got back to discriminant. It's really going backwards, isn't it? B squared minus 4ac. And we've got proof that these things are fine. Yeah, I would do it like this with the determinants. Determinants of matrices. They're 0, 1, mod 4. Positive definite if f. Okay, oh, so positive, this is an easier way to remember it. Positive definite says it's always positive. That's much easier. Easy, clearer why. Clearer why it says this. Always positive or 0. A and C must be positive, that's true, but there's more that we can say. In fact, it's enough to say that A is positive and D is negative. So is there a way to write a quadratic form that makes it more clear that if D is negative, you can make the thing take negative values? Must be, that's sort of the point. I'm no longer sad about this. Yeah, no, here it is. There it is. It's this. Yeah, so it's clearer now if you write it like this. What a crazy way of writing it, but hey. 2ax plus by all squared plus something that could be negative. Then you could, oh, can we actually put integers in to make that kind of 0 or small? What's the point of this? Yep. So these are the cases like this. If D is positive, then what do? Oh, some square roots have appeared. This looks fun. Oh, difference of 2 squares. If D is positive, then difference of 2 squares. Now I'm looking for evidence that this is actually a negative number, or could be a negative number. And what are we going to do here? So there's a bit of factorisation. B minus root D over 2a. They've pulled out a factor of 4a squared. But it looks a bit messy. X minus d is y, x plus minus 5y. Yep, cool, those are different. X over y is less than theta and less than phi, or both. So 4af of xy is positive. But if x over y, okay, so splitting the ranges up. It's not obvious to me that x over y, oh, you could, whatever theta and phi are, even though they involve weird, even though theta and phi have all these weird square roots and are kind of like real numbers, you could make x over y be anything rational, but there are loads of rationals in between, even the weirdest thetas and phi's. Look, so here, in between theta and phi. Okay, it's a bit of a messy proof, but fine. This thing is This thing is sometimes negative, sometimes positive. Kind of want to plot that. What do I want to do? Oh, so this is 0 on a pair of lines, and then it changes sign across the lines, right? So this expression here equals 0 on this pair of lines. X is theta y, or x is phi y. I don't think I've drawn those the right way around, but whatever. And then so it changes signs depending on whether as you cross the lines in these different regions. Okay, these are axes, the other two are lines. Anyway, okay, good. And I was a bit worried that there wouldn't be any integer points in the interesting region, but in fact there's loads of integer points, like way out here. Integer points are great, with the kind of appropriate ratio, x over y being maybe you want between theta and phi, kind of like a saddle. Okay, good. It always scares me a bit when I see these like square roots coming up in my whole number theory course. Don't really like that, but hey. Okay, I think I found the stuff that I don't understand as soon as I read it. So I think I'm in my zone of proximal development. ZPD. Let's go. Minimum coefficient. Right, here's some transformations. These have that has determinant 1, and it does this weird stuff to the matrix. Let us calculate. Is that transpose thing the inverse? Am I being daft? 0. Not quite. Not quite. Chat, how do matrix inverses work? I'm not joking. You want something like this, right? And then you put minus signs in. DA minus BC, AD minus BC, and you get DC minus DC, you get minus AB, and then you get an AB. I worked it out. Chat, I worked it out. AD minus BC. So you have to divide by AD minus BC in this world. Whew. In this world, yeah. It's not just this thing on the left with the transpose is not just the inverse, right? Because we're supposed to flip a bunch of extras. Oh, but these things are equal. Oh, hang on. I'm getting there. Why is there a transpose over here rather than... This is just really basic, I'm afraid, but I was kind of expecting an inverse for like the inverse transformation. But the inverse is actually different, isn't it? It's this. Yeah, okay, so it's not an inverse. Not inverse. And when I was trying to understand it, I was saying inverse quite a lot. And I was thinking about going the other way in this transformation over here. That's not what's going on. ZPD. Okay. Right. So I can worry about that a bit more, or I could try and push on a little bit further and see if it gets more clear with more experience. Revision. Determinant of a 3x3 matrix. Oh my goodness. Do I even know how to do the inverse of a 3x3 matrix? Matrix of majors and minors or something? It's been a while. So I think you do something like you cover up the right column, you write down the determinant of the 2x2 matrix that remains, you maybe put some plus and minus signs in for spice, and then maybe put some plus minus signs in for spice and divide by the determinant. That's my vague understanding, right? See if we can do it. So my vague understanding is that I'm supposed to write down something like EI minus FH here, and then something like DI minus FG, but actually the other way around. And then I'm supposed to write over here something like DH minus EG, and divide by the determinant, which is going to magically work out, right? Because it's AEI, A times this, plus B times that, plus C times that. Alright, maybe these are going down. Maybe I'm supposed to do this transpose. Yeah, probably transpose. I've forgotten to transpose this, don't I? Let's put it in here. So that when I multiply, I'm going to get the right matrix. Yeah, thanks, Neutrino. And then I want to do the same thing, and it will just all work out. For example, this one's the easy one, right? He's AI. Oh no, he says easy one. That's a stupid thing to say. Never say it's the easy one, because you will definitely make at least 3 mistakes while writing it out. Over here, AH minus BG, but can't trick me. I'll write BG minus AH. Up here, looks like it should be, so ignore the row and the column. Look at DI minus FG, but actually write the other thing. I haven't remembered to transpose. I've just walked straight into the same trap again. BI minus CH, but can't trick me. CH minus BI, and then in this corner, look over here, cross it out, BF minus CE. Oh my goodness. I keep going. Can I sort of check that this row? Yeah, so maybe I should check what happens with this on the other rows to check this is going to give me 1, 0, 0, and that'll be convincing enough for me to think that I've got along the right lines. So it's going to give me DEI, but this time it's going to give me minus DEI. It's going to give me DFH, but this time it's going to give me minus DFH from the first one, DFH from the last one. We're all good, I think. Can I be bothered to write out all 6 terms and check? No, something like this. Let's keep going. What's down here? So look, transpose, remember the transpose, cover up the F, cover up the column and the row, look at the remaining terms, AH minus BG. But this is on a kind of -1 sort of situation, so we're going to write down BG minus. I still am messing up I'm still messing up the transpose constantly, but without being able to stop at all. Oh, I think we're getting close though. AE minus BD or something. Oh, I didn't enjoy that. Yeah, definitely revise this sort of thing. Maybe if I avoided that less. Oh look, we've got back around to a thing we were looking at before, because now we're at lemma 33. Have I skipped the thing about reduced? Yes, I think I have. I skipped a page. That's why we got back. Okay. So a couple of special relationships here. Substitution. Yeah, okay, calculation. You can flip the sign of B. If you also switch C and A. Okay. Every positive definite binary quadratic form is equivalent to a reduced form. And here are some substitutions to prove it. I'm kind of interested in when we use the fact that it's positive definite, but you know. If A is bigger than C, use S to decrease A while keeping B fixed. We're trying to make A smaller than C. If A is smaller than C and B is too big, then use T plus or T minus. So these things above were actually exactly the things that this proof wants to use. Repeat these steps as long as necessary. Each step decreases. Yeah, okay, you make progress. While keeping it positive. That's important, isn't it? Good thing we're positive definite. And we've got A is positive. This with will be less than equal to A, less than equal to C. That's what we want, right? No, what's this? Oh, the last one. If B is minus A, I think you could do one last flip. T plus. Let's have a look back at what T plus was doing. If B is minus A, then this is, you can flip it to B plus 2A again to get a positive A here. While this thing b is minus a will go to stay at c, stay the same using t plus. The plus signs in that expression, I think. Leaving the others unchanged. Okay, so you can do a special flip. So that seems a bit amazing. Oh, okay, so it's only if b is minus a. So this is saying that ax squared minus axy plus cy squared represents the same numbers, or is equivalent to ax squared plus axy plus cy squared, and the relationship is simple. It's t plus, which says look at t plus says look at x plus y and y as the two things. So if I read across the columns, is that what it says? Yep. If I dot things with x and y, that's that working. So it's something like the substitution like this. Brackets x plus y, y plus cy squared. And then this is going to sort itself out magically, I think. Right, because there'll be an ax squared here, which is what we wanted. A 2axy, and an ay squared. And then this thing will subtract off magically axy and ay squared. So get rid of this nonsense and leave me with axy. So you start with minus axy and you get plus axy. That's a good switch. I like that a lot. And it leaves the cy squared alone. I should write it down at the end here, but it leaves it alone. Huh. Okay. That is what it takes me to write to understand this. I've got to go and do it, right? Read back what t plus is, stick it in, check that it works. Oh, yeah, all right. There's a general formula in there about what t plus does in general, but in this particular case, I can write something up to check the sense of it. Okay, and this is, I think, playing around with the case where, this kind of special case where mod b is equal to a. A is equal to c, apply s if necessary. Let's try and understand that one. If a is equal to c, then apply s. What is s? So s is, says look at minus y and x as your substitution. So that's going to change the sign of b and swap around a and c by kind of swapping the roles of x and y, and also free minus sign in there to make the middle coefficient non-negative. Okay. Good. And then so this bit is the start of the proof that this is unique by talking about whether these things are equal. And I should read all of the text here because this is the thing that I was having trouble with in a couple of pages' time. This kind of equivalence and the idea about it taking values and that revealing stuff about whether they're equivalent or not. I've now got this understanding that equivalent forms should do the same values up to. Not sure about this transpose matrix thing. I should probably write out some matrices at some point. Not quite sure I've got that, but I get the idea that they should take the same values because you can do some substitutions in both directions. Okay. What can we say about the small numbers it represents? So this will be a bit of a giveaway because if one of them can represent some small numbers and the other one can't, then there can't be any substitutions that get between the two. Right. So f of. So I saw later on we're looking at f of plus or minus 1, 0, which means you plug in x is plus or minus 1, but you're going to square it, so you get this. And c is 0. So, no, y is 0, sorry. So ax squared plus bxy plus cy squared is just a. Good. So there's a bit coming up later which talks about the 4 points, and I guess these are 4 different values of x and y, so we give you 4 different like pairs. It's a bijection in the pairs, if I imagine these being like u and v substitutions instead of x and y over there. Don't love it. I suppose we'll get there when we get there. I don't know why I wrote this all out again. What if neither variable is 0? Yeah, good. Okay. Here we are. We've got a 3x3 matrix, which I'm just going to shuffle off the top there. Smallest integers represented by f are coprime xy, or the pair of zeros. Why are we looking at coprime x and y? Feels like to me, if the numbers are coprime, then you can make a smaller value by. Oh, okay. We're going to list several small values. Yeah, okay. Okay, so here are some values. If x equals 0, coprime mathematical conditions forces y to be plus or minus 1. Sure. Okay, wait, so what are they trying to ban? They're trying to ban me from looking at what's going on at 2, 0. So, not 2, 0. Why are they trying to ban me from looking over there? Well, I suppose the result's not going to be true if I look over there. So maybe you can make another small number in some cases. So I'm going to write down something reduced, which means that B could be 0, but maybe A is much less than C. Yeah, okay. And then the smallest numbers that I can make are actually, if you put in 1, then you can make the number 3. If you put in the number 4, oh, sorry, x equals 2, then you get 4 times 3 is 12, which is smaller than 17. And the claim is going to be that C is the next smallest thing that I can make. Okay, so this is trying to ban me from the case where one of my coefficients is just huge, so I get lots of small values. Okay. As by restricting the values that we put in, call those coprime because they are coprime. Okay. Getting there a little bit, I think. Okay. I like these kind of little examples. I also like to erase them so that when I come back, I remember that they're not important. I don't sort of want them cluttering up. I should probably delete that 3x3 matrix that's in here somewhere. There it is. So that I remember that that's not actually relevant to what I was doing. Also because I'm suspicious that I might have got some terms wrong and people might look at it. Good, gone. Okay. 10 to 4. Let's see if we can understand the smallest value thing. Yeah, sorry, 3x3. That's now homework for the viewer, I think. If you need a 3x3 inverse, please work one out from all of the weird maths that you have to do to get there. Okay, so I agree that these values can be taken. And then I want to look at, okay, so what happens if these things are both positive? And first we're looking at x bigger than y, later we'll look at y bigger than x. So there's a lot of mod signs appearing. Bigger than or equal to negative, I agree with this. This is the worst that could happen if you subtract stuff. And some mod signs have appeared because, mod x is bigger, so it would be even smaller if you subtracted bx squared. Mod b, mod x squared. And then factorize like this, which is then greater than or equal to. So these things are both well, this thing's still really positive, right? So a minus mod b is positive, is greater than or equal to 0, I think. It's because it's reduced form. I think that's true. Yeah, mod b is supposed to be smaller than or equal to a. We might have written it like this before. And then less than or equal to c as part of our what does it mean to be reduced statement. Okay, so these things are positive, and these x and y things are at least 1, so just write down the smallest thing if you put 1 and 1 in both of them. So is this quite a roundabout way of checking what's going on at... Okay, so you've got the origin, we've plugged that in, we've got 0. Then you've got 1, 0. If we check that, you get A. We've got 0, 1. We've checked that, you get C. And we're banning these for not being co-prime points. So next up, we're looking at... Oh, we've got some negative things going on as well. We've looked at these. Same values. Yeah, if one term is 0, the B stuff doesn't matter. We've banned those as being not interesting, so I think we're looking at different signs of stuff. Are we just looking at these 4 points? Is that all that's going on? Because our end game here is to plug in 1, 1. I suppose we're trying to prove something about everything over there. So maybe you could do this as 4 quadrants or something. We're banning all of these points. So you could say, aha, looking at all of these things over here. So that's the case where x and y are both positive numbers. Then the value of all of these is larger than in this bottom corner, which kind of makes sense. You're making x, y, and maybe y are larger as well. Okay, b might be a negative number, so that's a little bit awkward. But it turns out that's the next smallest when you plug in 1, 1. Yeah, okay, so let's try plus or minus 1. Y is plus or minus 1 independently. Then f is a, because this thing will be squared, plus 1 is b, plus c. So if I want a small thing, I should subtract mod b, whether or not b is positive or negative. I should choose whichever sign makes this a kind of subtraction kind of prospect. So definitely larger than c. Yeah, because a minus mod b is positive. Good. Since f is reduced, we have this. Choose sign depending on sign of b. Good. Okay. That's the next smallest thing. We're kind of looking near the origin and then looking around to see, oh, what's going on next. And A and C might be quite different, so the values are kind of biased in that way, but by being larger, if C is huge, then the values just get really large as you move in the vertical direction. I'm imagining these to be my A and C. Oh no, this is X and Y. This is X and Y, and then if you move in that direction and C is huge, then CY squared just blows up really large. So it's kind of biased, it's not symmetric as a picture, but we should still look at these by points. Okay, do I like this proof? Don't love it, but I think I accept it. Okay, we're back at Theorem 34, but now with a little bit more experience, memory of what's going on. Let's have one more go at this, and then maybe call it a day. Equivalent to a unique reduced form. So, smallest non-zero integer. So why don't we just look at the next one, the next smallest non-zero integer, which feels like is going to be C, right? Next smallest. So just say that C is equal to C prime. Why can't we just do that? Why are we talking about these 4 pairs must correspond to the 4 pairs of F prime? Oh, what if A is equal to C? Is that what we're worried about? Yeah, so we're looking at these 4 pairs. Yeah, I don't think I understand this pair of lines where it doesn't just say look at the next smallest thing. Okay. And then there's a bit here to talk about whether B prime is equal to B. And I think we're pretty close, right? Oh, but there's this like reasoning, like if B is positive, can these both be reduced forms? And it's like, no, right? A is less than C, because then if they're equal, the middle thing has to be non-negative, so we'd be done. What B has to be less than A? Well, B has to be less than A. We can't have B be negative A. So, oh my goodness. Here we go. Grand finale of understanding for today, I think. Can I get where these inequalities have come from? A is less than C is less than A minus mod B plus C. This is the conclusion that I want, right? What function is this? Oh, the proof that we did for when this thing takes these values didn't say where it takes them. So now we're doing that work now, I think. And then what's this? Big picture. Okay. If the two forms are equivalent like this, then what's the substitution? So then they're going to be actually equal. And this is all work to show that B is 0. Okay, that inequality on the page turn seems pretty tough. Let's give it another go. I'd have thought this was just impossible because, what do I think? Oh no, okay, so I was going to say because mod B is less than A, but that's fine. Mod B would be less than A in both cases, right, if it's a small number. So we're imagining whether 2, 1, 3 and 2 minus 1, 3 are both examples of reduced things. Can they both be reduced? And that's not be reduced as a verb, that's reduced as an adjective. Reduced form is something we say about forms. We say that they're a reduced form if they satisfy certain conditions. And one of them is that if A is actually less than C, then yeah, both of those look fine to me. Oh, the question is kind of, can these both be reduced and equivalent, right? We kind of accept that there might be different reduced forms that look pretty similar. Same discriminant and stuff, and same, both satisfying the inequalities. The question is whether they can be whether they can be equivalent via some like weird PQRS matrix. I think that's my understanding of what's going on here. Do I really think these are both reduced? A is less than C, mod B is less than A. Yeah, they look reduced to me. Didn't we have a switch for this? For oh, we'd swap C and A. One of the switches that we had before. Over here, only back a page. Oh my goodness. We're going to switch for this. Let's see. Will be no. If B is negative A, we do a switch by leaving the others unchanged. Oh yeah, okay. So I was imagining this sort of thing, but that's an extreme case of B. B is actually equal to minus A. Right down here. Both reduced. So this is just what it means to be reduced. Mod B is less than A, less than C. Can I have B is equal to minus A? Can I have B equal to minus A? There's an exception, I think, where you can have B equal to minus A. Oh no, we use this. That's when we use the switch to make it positive. So why do we write mod B less than equal to A less than equal to C as a summary of being reduced? I've seen that somewhere else. Am I just being a bit wrong? Yeah, it's two cases. We cannot have B equal to minus A. That's just not part of being reduced. Okay, cool. Cool. So my memory aside, you're just not allowed to have B as equal to minus A. Oh yeah, so okay, we're writing this as a shorthand. This is necessary but not sufficient to be reduced. So it's useful if you're trying to prove something about reduced form, then you could just say this is true about reduced form. It's necessary that they satisfy this condition. This is a little bit weaker than what a reduced form actually is. New understanding. Good, that's what I was aiming for. And then this is going to check, aha, are they equivalent? We know some points correspond to each other in what I think is the obvious way, but hey, where does it take those values? Those are going to correspond because that's where it takes those values. And then the matrix has got to, if these are actually equivalent, the matrix has got to be pretty weird. It's got to be the identity or negative, so be the 0. Okay, I think I'm getting there. We're working through a little bit. I'm going to update the map a tiny bit with my zone of proximal development stuff to go. I think I'm getting there with this. I've got a little question mark around the transpose rather than the inverse, but I'm giving myself a tick. And I think I'm giving this a tick, but like an exclamation mark. It's not quite what you think. And I'm giving this a bit of a tick as well, I think. Like pushing the boundary here of what I understand. Maybe next time I come back to this, it's time to look at finitely many reduced forms with discriminant D. Or maybe jump somewhere else and try and explore and find other things to help me motivate what I'm learning. Gosh, right, okay, we've got some learning theory going here. Good, okay. I think I'm wrapping up. Thanks for coming with me on this journey of learning number theory, chat. I'm enjoying understanding more about, well, quadratic forms a bit. X squared plus 1 a lot. I really do want to understand. I think we're getting there. When is -1 a square number? There it is. There is a number which squares to something which is 1 less than a multiple of 289. It is $38, because 38 squared plus 1 is a multiple of 289. Oops. That's never going to be not funny to me. Look at that, 38 squared is one less than a multiple of 289. Brilliant stuff. So 38 is kind of the square root of -1 in the mod 289 universe. We've got a way to calculate that out. I think we're kind of there on when is -1 a square number in modular arithmetic, because we've got an idea about prime powers now, and I think we can combine it with Chinese remainder theorem. Yeah, but there's more here about sums of two squares that it seems like we get. The reason I'm going to keep going back to this, I think, is that the sum of two squares stuff feels like almost a kind of free add-on, that if you understand x squared plus 1, that you can use a kind of equivalent representations facts, these ideas about things, oh, this sum of two squares thing is sort of very similar to x squared plus 1. So I think I've got things I know, including when is -1 a square number, maybe just outside what I can properly say I understand. But it feels like lots of interesting stuff in those zone of proximal development about sums of two squares, which is just cool. What's the possible norm of a Gaussian integer sort of stuff, which I might as well pick up while I'm here, while I'm learning this sort of stuff, even though it involves learning a lot of binary quadratic form mathematics, not all of which I love. Thanks, man, Ash. Making progress. Okay, I will see you around in another live stream at some point. We're live for a professional live stream on Thursday, an unprofessional live stream on Saturday. I hope you have a lovely rest of the weekend. Enjoy your week. Bye. Bye. I can see Neutrino and Herb and Mountain Ash and Mary and... Yeah, did I say Saturday? I meant Sunday. Let's try that again. We're doing a professional stream on Thursday at work, and I'll do my unprofessional personal stream on Sunday afternoons, just like this Sunday afternoon. Thanks, Herb. I'll see you around. Have a good one. Bye. Ooh.